Okay, sounds good. So are there any questions from last time, from the two classes you had last time? Any questions from the Zoom audience? Are you online? Okay, so last time we discussed the Noether current, and we discussed the stress tensor, right? And that's where we concluded. And I showed you how the Hamiltonian and the momentum density you could also think of as integrals of t00 and t0i, and the fact that the Hamiltonian was conserved, you could trace back to the fact that your theory has a symmetry under time translations. The fact that momentum is conserved, you can trace back to the fact that your theory has a symmetry under spatial translations. Okay, good. So now we want to discuss some other charges that were in fact discussed, already brought up in the questions last time. And one of them, so we now want to discuss charges under right. So before we discuss how Lorentz transformations act in fields, I just want to remind you what Lorentz transformations are. Right? So Lorentz transformations are transformations where you take some vector. This is a 4 vector, right? Okay. And you transform it this way. So you take a vector which is x mu, and you transform all vectors in the world in this way. This is some generalization of the rotation. And the key point that you want is, let's say I write x tilde mu is equal to this. And you want that x tilde mu, y tilde nu, okay, y tilde nu, eta mu nu is equal to x mu, y nu. Okay. So Lorentz transformation is the thing that preserves, inner products under, it preserves the inner products of 4 vectors, just like rotations are things that preserve the inner products of 3 vectors. Okay. So this is the important property that Lorentz transformation satisfies. So is this clear? Okay. So we want to understand, what the charges under Lorentz transformations are. So for this, we want the infinitesimal version of a Lorentz transformation. Okay. So let's think of a transformation that does. This is our small parameter as usual. Okay. And of course, you could have higher order terms, but I just want to ask, I want to consider a small Lorentz transformation. That's why I'm considering a transformation in which x mu kind of goes to x mu to first order or to 0th order in lambda. And then, here's a first order term. Okay, so it changes slightly. Is that clear? Okay. So we want to ask, and this is the most general kind of transformation you can make of these coordinates x. Okay. Provided you can, of course, shift the origin, you can make translations, but that we already discussed. So this is, the most general kind of transformation you can do, because see, I'm writing x mu goes to x mu plus an arbitrary tensor times x mu. So this is the most general linear transformation that you can make for these coordinates x mu. Okay, you can make other kinds of transformations which are nonlinear, but at the linear level, this is basically what you have to do. Yeah? Okay. So now we want to understand what are the properties of this epsilon mu. Okay. Okay, how do we figure it out? Well, we figure it out by using this property of the Lorentz transformation, which is that the inner product should be preserved under this kind of transformation. So we want that okay. Just look at this equation and notice that I've been a little careful about raising and lowering indices. Okay. So on this side, y mu has the mu index lowered. Okay. Correspondingly, the epsilon tensor also has the mu index lowered. Okay. On this side, x mu has the mu index raised, and the epsilon tensor has the mu index raised. This epsilon tensor is just something right now. Yes, we're going to figure out what it is. Okay, good. So we want these two sides to be equal. But what is this? Okay. And then we get two terms. We get one term which looks like okay. And then we get another term which looks like So, and then there's a plus order lambda square term, but we're not going to keep track of that. We're not going to keep track of that because we haven't kept track of the transformation to order lambda square. Okay, so we only want this to be true to order lambda. Okay, is that fine? Okay, good. Similarly, we want this equation also to be true only to order lambda. Okay, okay. Now, look at this term here. Okay. Now, in this term here, I have one index raised and one index lowered. But I could lower this index and raise this index. That you're always allowed to do in contractions. Okay. Now, x mu y mu is the same as what we have on the right hand side. Okay. And therefore, what this means is that okay. How can this be true? Sounds like it could never be true. But in fact, it can be true by realizing that these mu and nu are in fact dummy indices. Okay. So I can call, in this term, I can choose to call mu nu and nu mu. You see that? So this is actually the same as writing well, what I've done is I've flipped what I'm calling mu and nu here. I've relabeled the indices. Now this must be true for all vectors x and y. Right? You could have some tensors where this is true. You know, maybe for any tensor you can find some vectors where this is true. But you know, you want to find a tensor so that this is true for all vectors, right? Because that's what a Lorentz transformation does. It preserves the inner product of all possible 4 vectors. And that means that epsilon mu nu is equal to minus epsilon nu mu. Okay, so it's antisymmetric. Okay. It's very important that both indices here are lowered. Yeah. This would not work, you know, if you tried to work with epsilon mu nu and try to compare it with one index upper and one index lower. Okay. Yeah.
We're allowed to do that only because we are working with Lorentz. And if there just takes value 1, 1, 1 minus. We're working in, let's say, non-flat space. Won't be able to do that.
We won't be able to do what?
So we had
this one. This we are always allowed to do because these are always dummy indices. You see, sum of mu, sum of nu, x mu, y mu. Who decides what you call nu and what you call mu? So you can always flip these indices.
So the second line,
this one.
So we have x with upper index, we have y with lower index, but in the next line we have written both.
That also you can always do. Upper and lower. No, but you see, when you have one lowered and one raised, you know, that you can always flip things, even if you have a general metric. By the way, you know, here in this class we are never going to have a general metric, okay? But you know, what you're trying to compute, let's say you're trying to compute something like this, right? Okay, this is what you would compute if you had a general metric. But this you can write as x nu y nu, or you can write it as x mu y mu. Okay, and it's equal to both, so you can choose which one to lower or which one to raise. Because of the I'm not understanding the question. This is the definition of what it means to have x nu, x rows. So you know, let's say you start with all indices. This is actually a question for a GR class, but let's say you start with all indices lowered. Then what does it mean to raise an index? It means you raise an index using this inverse metric G. So this is just a note, you know, this is what it means to raise and lower indices, means that you have a metric G with which you raise and lower indices.
So what I'm asking is,
yes.
We have one upper index, we have one lower index.
Yes.
We can lower this index of x if we act with a metric, like we are doing this. If we have both upper index and if we act with a metric.
You're asking why this is equal to this? This is what you're asking, right?
Right.
Yeah, this is equal to this. This is always equal to this. Is what it means to raise and lower indices. is that you're always, you see, what does this mean? So let's say we start with all indices raised, for instance, right? What does it mean to lower the index? It means to act with a metric. Right? That's what it means to lower the index. And similarly, so when you have one index raised and one index lowered, you can always decide which index you want to raise and which index you want to lower. You can, that's what I was saying here. So here this x index is raised and y index is lowered, but that's also the same as the x index lowered and the y index raised. So here the mu index is raised and the y index is lowered, but I can lower the y index and raise the new index. Okay, that's free. Did I make a mistake in what I wrote here? Did I flip something here? No, I didn't, right? Well, wait a second. Did I flip? No. Sorry. First of all, this term came from here. Yeah, because one term went away, and this term came from here. I don't know that's what was confusing you. This term came from here. This is the x mu y nu term. This actually I didn't do anything, but in this term I raised, I lowered the x and I raised the. I lowered the mu here and I raised the mu here, and that you can always do. Yeah. Okay. 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 Are there more questions about this manipulation? Okay. Okay. So this is the defining feature of a Lorentz transformation, which is this. Okay. And this is it. There is nothing else. You give me any antisymmetric tensor, okay, and that defines for you a Lorentz transformation. Okay. So Lorentz transformations are defined by antisymmetric tensors. Okay. There are 6 such antisymmetric tensors you can write down, right? 6 meaning, because you can always construct more general antisymmetric tensors by taking linear combinations of these guys. But there are 6, and that's because you can write down epsilon 0, 1, epsilon 0, 2, epsilon 0, 3, and then you can write down epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3. Okay, so you can choose those values to be what you like, and then the values with the indices flipped gets fixed. Okay? And the diagonal values of these epsilons have to be 0 by this constraint. Yeah. Okay, so this. Yeah.
That epsilon mu equals to epsilon minus mu, that you said that indices should be always in the lower, right?
Sorry, here for this property to be true, yeah.
Or
both indices you can raise also. Sorry, you can raise both indices, it would still be true, but you shouldn't try and look at one index lowered and one index raised.
Yeah, right. Because some of the books have mentioned to the upper indices to be antisymmetric. Like
it's okay, yeah. You're always, you can, if you have all indices lowered, you can also think of all indices raised. It's the same.
Is there any like physical significance of this? Why this infinitesimal Lorentz transformation is antisymmetric?
It's not a question of physical significance. It's a question of a tensor having some properties, when you lower all indices, right? When all the vectors either transform covariantly or contravariantly. I mean, I don't know what more physical significance to ascribe to it, except this is a restrict, it's not like you have more than 6 tensors. Maybe when I do an example, it'll become clear. If you raise one index and lower one index. But whatever tensor you have should have the properties when you lower both indices or when you raise both indices, it's antisymmetric.
Oh, yes.
Okay, let's do an example. Let's first consider the tensor which has sign conventions match. Yeah. Okay, this is a possible tensor. All other by all other I mean everything where you don't have mu and nu equal to 1 or 0. Okay, this is a possibility. Clearly satisfies what we have above, right? Because minus of 0 is 0 and 1 minus of 1 is minus 1. Okay, good. So when you look at this tensor, you can then ask, what happens if you look at epsilon 0, 1, and that's still 1. Okay? In sign conventions you're using. On the other hand, when you look at epsilon 1, 0, what is that? It's also 1. It's also plus 1. It's also plus 1 because you raise something with eta 1, 1, which in our conventions is negative. Okay. So epsilon 0, 1 is equal to 1 and epsilon 1, 0 is also equal to 1. Okay, so notice I said you have to be careful about flipping indices, and this makes sense when both these indices are lowered. Yeah. Okay, good. What does this mean? You see, what it means is that you look at, just looking at the transformation above. Remember, the transformation above was x mu goes to x mu plus epsilon mu nu x mu, right? Plus lambda times something. Okay. So let's say you look at delta x mu, that is equal to, in this case, it's equal to lambda delta x0 is equal to lambda times epsilon 0 1 times x1, which is equal to lambda x1. Okay, so x0 changes by x1. Okay, what is delta x1? Well, it's equal to lambda into epsilon 1 0 times x0, also equal to lambda x0 with a plus sign. Okay, and the plus sign is important. Infinitesimal. Okay. Is there an I here? There's no I here, right? Always harder to spell on the board. Okay, this is the infinitesimal version of a boost, right? And the boost is just x0 goes to cos phi x0 plus sinh phi x1, okay, and x1 goes to cos phi x1 plus sinh phi x0. Okay, or alternately x0 x1 and x2 goes to x2, x3 goes to x3, right? So x0 x1 goes to cos phi sinh phi cos phi. Do you see why this is the same as this to leading order? If you just expand it out to first order and lambda, you just put phi equal to lambda and make it very small, and you will see this is the same. Yeah. Okay, what is this transformation? Have you seen this transformation? This is a boost, right? This is a boost in the x1 direction. So this is, this is exactly what, let me see if I can remember the formula. When you write, when you write t goes to t plus vx into 1 by square root of 1 minus v squared, okay, and you write x goes to x plus vt into 1 by square root of 1 minus v squared. Okay. So this is, the same thing. I hope I got that right. I think that's right. Yeah. So this is, this is a boost, and this is just the infinitesimal version of that. Here is the boost written in terms of a velocity. It's just a Lorentz transformation. Okay. And here the boost is written in terms of angle phi. That makes angle phi is kind of more used, but this is how you're taught in elementary relativity courses. Okay, good. So this is a boost in the one direction, and of course you can boost in the two direction or the three direction, and those are all Lorentz transformations. Yeah? Is that clear? Okay, good. What about other kinds of transformations? Let's say you look at epsilon ij, right? So you could also look at other rotations, which are epsilon, for instance, 1, 2 is equal to 1, and epsilon 2, 1 is equal to -1. That's a possibility. That's another possibility. Now what happens? Now let's say you look at epsilon 1, 2. What is that equal to? That's equal to -1. And what is epsilon 2, 1 equal to? That's equal to +1. Exactly, right? So now this becomes -1 and this becomes +1. Right? Okay, good. So now notice that in this case you have 1 -1 and 1 +1. Whereas here for the boost you had both +1s. Okay. So for this case, what is the transformation? Well, the transformation is delta x1 is equal to minus lambda x2 and delta x2 is equal to plus lambda x1. Yeah. Which is the infinitesimal version of a different transformation, which is the infinitesimal version of x1 goes to cos theta x1 minus sin theta x2, okay, and x2 goes to cos theta x2 plus sin theta x1. Okay. And the minus sign in the middle is important because that's what ensures that both determinants are 1. Okay. This determinant is also 1 because cos square phi minus sin square phi, since cos square phi minus sin square phi is 1. And this determinant is also 1 because cos square theta plus sin square theta is 1. Okay. So here you have a minus sign, here you have a plus sign, but this is a rotation. And so indeed, what are Lorentz transformations? Lorentz transformations are boosts and rotations. Okay? And you see that this index, this tensor that we set up, which was antisymmetric, is sufficient to get for us all kinds of rotations and boosts. You can consider more complicated tensors, which would be complicated combinations of rotations and boosts, but you see this generates everything. Yeah. Okay, good. So now this is also a symmetry of the theory, right? In fact, this is the reason why this course exists, right? Because boosts are a symmetry of the theory. Otherwise, we wouldn't have this course because the whole point of this course was to say we want something that makes sense relativistically. So this is a very important symmetry of the theory, and we want to work out what the charges corresponding to this are. So the first question is, how do the fields transform? So how do the fields transform under this kind of transformation, right? Which is delta x mu is equal to lambda times epsilon mu nu times x mu, right? So how does the field transform? Well, you know how the field transforms. Because the field just transforms, that's what a derivative means, right? You make a small transformation in x, it's the same as making a small transformation in the field by this. Okay. Again, you have to be a little careful about active and passive. Whether you should, if you put a plus sign here, and depending on whether you think if it is active or passive, you might want to put a minus sign here. That's completely irrelevant for what we're about to discuss. Okay, there's some active-passive convention you might want to be careful about, and in this class we're just choosing whatever makes these signs correct. Okay, good. So this is the change in the field, right? And sorry, there's a lambda here, and this is the object that we are calling d phi. Remember, there's an object that we call d phi, which is the coefficient of lambda, and this is the object d phi. So what is the Noether's current? We have J mu is equal, well, one more thing. What about the change in the Lagrangian itself? Is the Lagrangian invariant under this? These Lorentz transformations? Is it invariant? Is it not invariant? Huh? Good. Okay. You see, the Lagrangian is also a scalar. Right?
It should be invariant.
Sorry, what was the question? Answer: it should be invariant. No, it's not, because
yes.
the action is invariant, of course, but the Lagrangian, under this kind of a transformation where you make a change of x is not invariant, because the Lagrangian density more precisely. Okay, the Lagrangian density, when you change x, when you push, look at the Lagrangian density at one point or Lagrangian density at a different point where the x's are related this way, those are not the same. Okay? And they're related how? So delta L is also equal to lambda into d mu L times delta x mu, right? Okay, and that is just equal to lambda into d mu times L times, oh sorry guys, I wrote something wrong here. This should have been d mu lambda times d mu phi times epsilon mu nu x nu. Okay, sorry, the lambda shouldn't have gone here. This is just obviously true, and this is what we call d phi. Sorry, just correcting the previous equation. I wrote d phi here. I mean, that's, so here I'd put a delta, and the conventions you're using is this. The lambda goes here. Okay. So notice that this is also equal to lambda mu del mu L into epsilon mu nu times x nu. Okay. What here? That's what you're saying, right? There's no lambda here, right? Yeah. Go on. Yeah. Is there a question from Zoom audience?
So, aren't we adding one total derivative term to the Lagrangian here?
Sorry.
Yes, sir. Am I audible, sir?
Yeah. Go on. Sorry, we can't hear you.
Sir, my question is, aren't we adding one total derivative term to the Lagrangian?
Yeah. That's what we're checking. Right now, this is what we've added. Yeah? So you might have said, well, this is trouble because look, this is doesn't look like a total derivative. This is d mu of L, but in fact, it is a total derivative, and you can think of it as okay. Why is that? Okay, that is because think of when you expand this derivative out, you'll get one term where this d mu acts on this, right? But notice that d mu on epsilon mu nu x nu is just equal to delta nu mu into epsilon mu nu. Okay. Now, if you like, you can lower one index and raise one index. This is the same as eta mu nu epsilon mu nu. But remember, eta is symmetric and epsilon is antisymmetric, and therefore this is equal to 0. Okay. So in fact, this term is a total derivative, as of course it had to be, because the action is clearly Lorentz invariant. Very good. So now we have all this is what we call d phi, and this we can call this is k mu. Yeah. This guy in the brackets is k mu. Okay, now we have all the ingredients to apply our machine and get the charges. Okay, and to get the charges, all we need to do is look at minus k nu. Okay. So let's consider the theories that we had previously. So let's make sure I'm getting my signs correct. Yeah. Well, this is just d mu phi. Okay. So this looks like d mu. Maybe I need more space. Well, let me just write this in the next. D mu phi times. We have to be a little careful about, there are lots of mu's floating about, so we have to be a little careful about the indices. Times d rho phi times epsilon rho nu x nu minus L epsilon nu x nu. Okay. Here I'm considering a theory where dl by d of d nu phi is equal to d mu phi. Okay. If that's not the case, you will have to put in the general whatever you can put in pi mu here if you like. Okay. But just for simplicity, I'm considering a theory where this is true. Okay. Okay. So now this looks a little complicated. However, we can make it simpler by writing this as d mu phi d rho phi x nu, okay, into epsilon rho nu. Write it as minus L into delta of second x nu epsilon rho nu, and I want to write this as delta of eta of rho mu. Okay. So I can, I can raise and lower the indices to write it this way. Okay. So I haven't done anything. I just relabeled the indices. In this case, this epsilon rho was raised. Okay. I lowered it and I raised the d rho here. Okay. In this case, the epsilon mu was just sitting here, and I wanted to write this as epsilon of rho nu times something. So I wrote it as epsilon of rho nu times eta of rho mu times x nu. Okay. In fact, it's the antisymmetric part of this that is conserved, right? Remember, because this is an antisymmetric tensor. So if you have a symmetric part here, it will not be conserved. I mean, that's irrelevant because it contracts to 0. So in fact, the conserved current that you get looks like d mu phi so the conserved current that we have looks like j mu d rho phi x nu, okay, minus L eta rho mu x nu, okay, and then minus rho goes to nu. Okay. So the same thing, but anti-symmetrized on rho and nu. And this is the conserved current for J nu. Okay. This conserved current, of course, depends on, these quantities are conserved for every value of rho and nu that you can pick, because they're conserved for every possible choice of antisymmetric tensor epsilon rho nu. Do you see that? So there are 6 possible such choices. Remember, because there are 6 possible antisymmetric choices of rho and nu. So there are 6 kinds of conserved currents that you get here. Okay. Now you might look at this and you might say that looks like a mess. It doesn't look like something I've ever seen before. It doesn't look like something we would recognize. However, it actually does, because if you compare this with if you compare this with the expression for the stress tensor that we found in the previous class, you will see that what we are actually writing is that okay, and that means that yeah. Okay, And this just comes by looking at that expression and seeing, that expression looks like x nu times some stress tensor minus x rho times, the stress tensor with rho and nu interchange. Okay. The stress tensor also had that form which looked like d mu d rho phi minus L times eta rho nu. Right? So this looks like x nu times t mu rho, which is this term, minus rho goes to nu, so minus x rho times t mu nu. Do you see? Okay, this looks a little more sensible. Okay, and this is indeed what is conserved. So in particular, we have 6 conserved charges, and the 6 conserved charges are okay. So you take this quantity, you put one of the indices to 0, you put, because the conserved charge is always obtained by setting the mu index to 0 and integrating over space, and that's what you get, yeah. Okay, good. Let's see what these conserved charges are in some special cases. So these are the, these are generally 6 conserved charges. Why are they 6? As I said, because you can choose mu and nu and rho in 6 different ways. Yeah? Okay. Is this all being clear, by the way, to everyone? Or there's some algebra here we are doing that's a little tricky, but just do it on your own to make sure it works. Yeah. Let's look at Qij. By this we mean spatial. Okay, so I want to put nu and this is a general formula for Q of nu rho, and I want to consider the case when nu and rho are both like some spatial indices. So you could take 1, 2, or 1, 3, or something else. Okay, or 2, 3. Okay, is that clear? So there are 3 possibilities you can do of this kind. You can take I to be 1, j to be 2, I to be 1, j to be 3, or I to be 2, j to be 3. Okay. Okay. What is this? Well, it looks like xi into t0j minus xj into t0i d3x. Does this look familiar to you? Yeah, it's the angular momentum. Why is this the angular momentum? Because notice this is, the momentum density in the j direction. This is the momentum density in the I direction. So the angular momentum, as you know, is actually associated to a plane. How would we write the angular momentum in class 12? We write it as r cross dp. So you look at some small volume, you look at the momentum in that small volume, and you do r cross dp, and you integrate. Okay, so you have some point, you have some p here, some small amount of momentum here, which I'm calling dp, and you just integrate. Okay, or if you like, r cross rho, okay, where rho is the momentum density, and then you integrate. Okay, let me write it in a way that makes more sense. So rho is, say, the momentum density in some direction, and that's how you would write it. Right? Notice this is actually exactly the same thing, and that's because even though you think of angular momentum as a vector, it's actually associated to a plane of rotation. Okay, and you see here clearly this is this is the momentum density in the j direction, and this is the momentum density in the I direction. Okay, so is it clear how this works? Okay, good. So this is the angular momentum. Last time somebody asked a question about Newton's first law of motion. So I want to show you how the Noether current in the 0 direction is actually that. Okay, now we have one more choice, right? We can also take nu equal to 0 and then take rho equal to I. Okay. This looks like x0 e of 0i minus xi, and now you get t of 0, 0. Okay, and this guy is conserved. It gives you 0. Very good. Now notice, look at this thing. Okay, this x0 actually is not part of the integral because it's integral of d3x really doesn't depend on x0. So let me write it in a slightly different way. What's the integral of t0i? It's the momentum, right? So I can write this as t pi. Okay, this is the momentum pi is equal to right. Okay, I can also differentiate this with respect to time. Remember, the momentum itself is conserved with time. Okay. So I can write this as when I differentiate this, I get 0 for dpi by dt, right? But I get 1 from here, right? So I'll find pi is equal to d by dt. I'm using t here instead of x0. T is actually the same as x0. Okay, so t is just to because we want to make it look like Newton's first law, and Newton didn't know about x0. Okay. Okay. What is this? This is just the mass density. Let me write it as x times rho. Okay. What is this quantity? Xi times rho times the integral of d3x. No, it's not the total energy. This is the center of mass, right? This quantity is the center of mass. It's the position of the center of mass. That's how you figure out the center of mass, right? You take the energy density or the center of energy. Mass is energy in relativity, and you integrate it with x. So you see the momentum is the rate of change of the center of mass. Okay, so that's how Noether's theorem gives you this relation. Yeah. Okay, good. So this is the center of mass in the I direction, and we see how the momentum is the rate of change of that. Okay, good. So that's what I want to say about conserved charges corresponding to Lorentz transformations. Are there any questions about this? If not, I want to move on to discuss a different kind of symmetry called internal symmetries. No, this is all in the quantum theory. Why classical? Where's classical? Yes. They might transform under some unitary, but they still transform this way. The commutative, not with the Hamilton, by Hamilton. So this is an operator Q, which is going to be a quantum mechanical operator, just like the stress tensor, the quantum mechanical operator. Yes. What does it mean? It will transform under some. Yeah. What does that mean? Okay, let's look at translations, right? So under translations, x goes to x plus a. Okay, there's a unitary, that's true, but that doesn't change the fact that phi of x goes to phi of x plus a. What you want to say is that u dagger phi u. This is the operator. In general, I'm not going to distinguish between fields and operators, but just for now, I'm putting phi hat. But that doesn't change the fact that phi of x went to phi of x plus a. So that's exactly what we use there. So there might be some unitary operator that will realize this, but what is the unitary operator going to do? It's going to do that. Corresponding to this unitary operator, if you write this unitary operator as e to the ix, then that quantity, which is delta phi, is the commutator of x with phi. Okay. So this is in the quantum theory. There's nothing classical about this. I mean, in the quantum theory, you have to be a little careful, and we won't get to that in this course, in how to define these t zeros. Okay. The subtlety in the quantum theory is that when you look at the expression you have for t0, you have the product of fields at a point. Okay, so you have d mu phi, d rho phi, and that product is being taken at a point. Okay, such a product always has to be regulated, as we discussed, because these fields are really operators, and taking the product of them at a point is subtle. And so, there's some literature, and this is an important thing, on how you regulate the stress tensor. So we discussed some simple ways of normal ordering, right, which had to do with just normal ordering and regulating things. In general, you might have to be more careful about how you regulate the stress tensor. Okay? But that's a separate story, you know, how you define these products. Other than that, this formula is correct. The fully quantum formula. And the fact that it transforms under unitary doesn't mean, it just means this. There is some unitary which does that. But the fact that phi goes to phi of x plus a is still true. Okay, good. Are there any questions? Yeah.
Sir, these charges and currents, these are locally conserved or globally conserved?
These are?
Locally conserved or globally conserved?
So the current is always locally conserved, right? Because it's d mu j mu is equal to 0. And the charge is conserved in time. So charge is something which is an integral over all space. And then d by dt of the charge is 0. But the current is locally conserved. I mean, that's what current conservation means. It's that, you know, its divergence is 0. Yeah. Okay, very good. Now, I want to look at a different example, which is an example that we call an internal symmetry. Okay, so these symmetries that we're discussing were kind of, you know, there were transformations of phi, but the transformations of phi were, you know, were being induced by actually transformations of x. Last time somebody discussed barrier numbers and so on. That's an example of what's called an internal symmetry. You know, but they're more familiar internal symmetries to us. For instance, just conservation of electric charge is an example of Noether's theorem when you apply it to what's called an internal symmetry. So what's an internal symmetry? So, you know, imagine, so you want to discuss now internal symmetries. So consider a field which looks like a theory which has two fields. Okay? Let me write this. Okay, this field 1 this is field 2. Okay. Okay. Where this is the same M. Okay, it's not there's no M1 and M2, but it's the same M. We could also consider other, like, you know, any interaction terms which would preserve this, but for now just think of this theory. Okay. This theory has a symmetry under, clearly it has a symmetry under phi 1 goes to phi 2. But in fact, there's a continuous symmetry, which is a symmetry under where you change phi slightly into phi 2. Okay, under rotations okay, this is not a rotation in physical space. We are not rotating anything in physical space. We are rotating one field into another field. Okay, so what does this mean? Well, it means phi 1 goes to cos theta phi 1 minus sin theta phi 2, okay, and phi 2 goes to cos theta phi 2 plus sin theta phi 1 for some value of theta. Okay. And then under such a rotation, this Lagrangian is left invariant. Why is it left invariant? You can check. You know, because what you have here is n squared by 2 into phi 1 squared plus phi 2 squared, which is the sum of the squares, right? And this is, you know, rotations we think of in space, but the rotation doesn't know whether, you know, phi 1 is you know, it's just a number for the rotation, right? So you know that x1 square plus x2 square would be kept invariant under this, and so even without doing the algebra, you know that phi 1 square plus phi 2 square is left invariant under this kind of transformation, right? Notice that's also true of this, of this d mu phi term, right? Because d mu phi 1 squared also transforms exactly in this way, right? D mu phi also transforms this way. So you see, there's a derivative here, but the derivative term also is invariant under this kind of transformation. Okay. So this is an example of what's called an internal symmetry. It's internal because there's no, nothing you're doing to positions to induce this change, but it's really, some change of the fields into themselves. So this is, I emphasize, not a physical rotation, but a rotation of fields into themselves. Yeah. We can consider what? Well, here the fields are all real fields. I'll discuss in a second what you can do. But for now, this is an SO2 rotation. Okay, you have only two real fields, not two complex numbers. So these are not complex fields; these are real fields. So what you have here is an example of an SO2 rotation. That's SO2, not SU2. Yeah. This is, in fact, as I'll say in a minute, it's an example of a U1 symmetry, not SU2. Yeah. Okay, good. So what is the conserved current corresponding to this? Well, this is in the form that we have with d phi 1 equal to phi minus phi 2, and d phi 2 equal to phi 1. Yeah. Okay. And what about the change in the Lagrangian? Yeah. So delta L is equal to 0. So there's no total derivative term here. So the conserved current is very simple to write down. Is just equal to d mu phi 1 phi 2 plus d mu phi 2 times phi 1. Okay, let me write it this way. I'm just interchanging the terms to make it look like. I did nothing between the first and second line. I just wrote it in a nicer way. That's the conserved current. And that's conserved. Okay. And there's a charge that corresponds to this. And the charge looks like okay. In fact, the familiar electric charge that we think of is of this kind. The charge that we see that's conserved around us is of this kind, although we haven't studied the standard model yet. So I don't want to go into more details about how this symmetry is realized, but it's almost exactly of this kind. Yes. I don't see how. What do you mean you don't see what is conserved? The Noether's theorem is telling us that you compute this and this quantity will be conserved. What you said regarding charge conservation or different charges? Yes. Oh. Good. Yeah. Give me a second. Maybe we'll see. You want to ask why doesn't it look like positive charge minus negative charge? That's what you're asking. Good. It does, but it's not evident now. Maybe it'll become evident in 10 minutes or 5 minutes. Yeah. Wait for some time. Are there any other questions? I'm going to postpone the answer to that question. I'll come back to it in a few minutes. Yeah. Go on. Yeah.
Sir, is the sign correct for the JMU?
For what?
For the JMU, is the sign correct?
The overall sign?
No, I think the second term should have plus and the first term should have minus.
That's completely up to you. The way I wrote it is that d phi 1 was minus phi 2 and d phi 2
Okay,
is
okay, yeah.
phi 1. Okay.
Okay.
You could have chosen d phi 1 equal to phi 2 and d phi 2 equal to minus
Yeah,
phi 1. I
minus
didn't
phi
put
1.
it because the way I wrote it here, I put a minus sine theta here. Okay. You could have put a plus sine theta here and a minus sine theta here. That's that's not important. Yeah. Okay, good. Now there's an important trick here which is related to the question that you asked, which is, these fields we have discussed so far have been real fields. Okay. However, it's often convenient to take real fields of this kind and combine them, two real fields of this kind, and combine them into a single complex field. Yeah. And the complex field, you can instead think of the field which looks like okay. And then what is chi star? Okay. And what is phi 1 squared plus phi 2 squared by 2? Yeah, exactly. It's just mod of chi squared. Yeah. What about similarly? This also looks like mod of d mu chi, the whole square. Okay. So we can also write the Lagrangian notice we don't write the factor of half when we do this because of the way we've normalized chi. We've put a 1 by square root 2 here. Okay. So conventionally, if you have a real field, it's normalized that way as half of d mu phi 1 squared. When you have a complex field, it's normalized this way as d mu chi squared. Okay, without a half. Okay, good. So what is the symmetry in this language? This symmetry that we have, what is it in this language? Yeah, okay, it's U1. What that means is that chi goes to e to the I alpha chi, and chi star goes to e to the minus I alpha chi star. For those of you who are not familiar with what U1 is, this is just a complex number, okay, which has, it's a phase, so it has mod 1. Okay. So you can think of it as a unitary matrix of dimension 1, which happens to have, determinant 1, which means its mod square is 1. Okay. And you can write the current, okay, in this form as well. We can think of d chi as being alpha chi and d chi star as being d of chi star. And so you can write the current as I times d mu chi star times chi, okay, minus d mu chi times chi star. Okay. Sorry, I shouldn't write the integral with the current. Okay. Sorry. And very good. You should, yeah. It's good. Okay. In answer to your question that you asked earlier about why it doesn't look like difference of particle number, this charge that we have here will look like difference of particle number once you expand things out in terms of creation and annihilation operators of these fields chi. Okay? These fields chi are the things that transform to themselves under U1 rotation, right? Because chi goes to e to the I alpha chi. So these are the fields that have a well-defined charge. This has charge 1 and this has charge -1. Okay, and when you expand this out, if you quantize these fields, you will see that this chi field contains creation operators of one kind and destruction operators of the other kind, as charge -1, and similarly for conversely for chi star. So when you expand out this kind of an expression, you will find it really does look like the difference of particles of positive charge minus difference of particles of negative charge. Okay. That's not clear in that notation because phi1 and phi2 are not actually the fields that have positive and negative charge. In this notation, chi and chi star are the fields that have positive and negative charge. Okay, so this is an example of what's called a U1 internal symmetry. We are not going to consider this so much in this course, not going to consider symmetries beyond this so much in this course. However, as you can imagine, it's possible to have symmetries of more complicated kinds as well. Have all of you seen some group theory, or maybe some of you haven't? Maybe some of you haven't, I'm guessing. Okay, so I just want to mention something. And okay, so we can also have more elaborate internal symmetries. Okay? For instance, let's say we have n fields, right? And we put them into a vector. Okay, let's call this vector capital phi. Right? Then these are just n fields, and I'm just writing them as a vector. Okay, so don't get confused by this. I haven't done anything deep. Every field gives you a number, right? So this is a function of x, and these are also functions of x. So now at every point, I have a vector. Okay? This vector is not a vector in physical space. Okay? All of these are scalars. If I make a transformation in physical space, this vector doesn't change. I mean, it changes, but doesn't transform like a vector, doesn't rotate like a vector. Okay, is that clear? So when we write vectors here, these are not vectors in physical space. Okay, good. Now, let's say you wrote down this capital phi transpose times d mu phi. Okay. Which means you take this vector, you differentiate it, and then you transpose it. By transpose, you just turn it into a row vector, and then multiply it with this. Okay. Okay. This kind of term has a symmetry not just under SO2, but under SON. Okay. And that's not surprising. If this vector notation is confusing for you, just think of three fields, right? We could have phi1, phi2, phi3, and imagine all of them had the same mass. Right? Then you could make various transformations like phi1 goes to phi3, phi1 goes to phi2, and so on, and you would have an SO3 internal symmetry. Okay? This is not just a property of free field theories. You could also have Lagrangians which have interactions, and if those interactions are invariant under these symmetries, the full interacting theory will satisfy this conservation of charge. Okay? Then there's no symmetry. No. Even for U1, you need at least two real fields, right, which have the same mass. So SON, you should just, SO2 happens to be the same as U1, but you should distinguish SON from SUN. Okay. Of course, you can also have SUN internal symmetry or UN internal symmetry, and it might be that take n complex fields. And let's call this, what should we call it? Z. There's no capital chi, right? Is it? And if you know what capital chi is? Okay, doesn't matter. We call it Z, yeah. Okay, so let's call this Z. And then, we can think of a Lagrangian which looks like d mu Z. Okay. But now I complex conjugate apart from taking the transpose. Okay. Okay. If I do that, this has UN symmetry. Okay. Okay, very good. So these are examples of more complicated symmetries, and of course you can have other, you can have other continuous symmetries. So you can have SPN, right? You can have also symmetries under these exceptional groups and so on. Okay. So every Lie group that you have, you can write down a field theory that has symmetry. Okay. Why Lie groups? Because we want continuous symmetries. You can also have discrete symmetries, but here we're discussing Noether's theorem, which applies in the case of continuous symmetries. Okay. Okay, excellent, very good. So this is what I wanted to say about symmetries. Okay, and Noether's theorem. Now I want to spend a little bit of time setting up for some description for the next lecture. Are there any questions about Noether's theorem and symmetries? Because now I want to switch gears a little bit and talk about something quite different. Okay. You're very quiet. I don't know if you haven't understood anything or if you've understood everything. Okay. Okay, so now we'll switch gears. We'll talk about different things. Okay. So far, we focused our attention on free field theories and on understanding free field theories. Okay. Okay. So now I want to say a little bit about interactions. Okay. Okay. Since we don't have so much time left, I'm just going to say some general philosophical things, and then we can will start discussing more physics later. Okay. So I want to say a little bit about sorry. I want to say a little bit about, what kind of questions can we ask in the presence of interactions, right? You see, the most general kind of question, we can ask very general questions, right? For instance, in the presence of interactions, we can say, well, prepare a state. It could be the vacuum or something else. Make some disturbance at X. Disturbance at X. And measure its effect at Y. This is the general kind of question we can ask in general, right? We can say, well, I have a field theory, and I have some disturbance. I do something here, and what happens somewhere else? Okay. And you might have thought that and in fact, when we do physics, often many other settings, these are the kinds of questions that we ask. Okay. However, it turns out that in field theory, in quantum field theory, you can ask these kinds of questions. I'm not saying we can ask these kinds of questions, but in fact, a lot of QFT focuses on something slightly different. Okay, what are those slightly simpler questions? Okay. The slightly simpler questions that we focus on, in fact, are the following kind. Okay. Where what you do is some free particles in the far past you allow them to evolve. Okay, they crash. So this is the kind of question that we often ask in quantum field theory. Okay, you prepare some free particles in the far past, you let them evolve, and then later you crash them, and later you get something out in the future, and you ask what that is. This kind of question is answered by what's called the S matrix. Okay? S for scattering. Okay? So it's like the scattering matrix. And this kind of question, is slightly, you might have thought it's slightly less general than this kind of a question. Okay? But in fact, it turns out to basically have all the information that you want about the theory. Okay? Now, why do we focus on this kind of a question, on this S matrix question? Okay, there are several reasons. And let me explain why we focus on them. The first reason, even though my experimental friends will laugh at me for talking about this in class, okay, so there's an experimental reason. Okay, and even though I know very little about experiments, I know a little bit about the history of experiments, and in fact, we have a rich history of learning about physics from these kinds of experiments. Okay, going all the way back to Rutherford scattering, which is how we discovered, after all, the structure of the atom, right? And going to the LHC today, right? Where also we're trying to do scattering experiments. So in all of these cases, we are not trying, and when Rutherford was asking the question, he could have asked a more general question. You have an atom and you do something and you probe it in some way, and what happens? But that's not the question that was convenient to ask. Rather, he said, here you have some target, you throw something at it, you ask what comes out. Okay, and that you use to infer something about the interaction. Okay? And that is also how we do particle physics today. Right? You crash particles together. You prepare some free particles in some beam, you let the beam go around, you crash it together, you get some other particles, you measure what comes out in the end, and then you try to infer what happened. Okay? You don't try and ask, well, what happens if you get like two quarks very close to each other, or two protons really close, so that you start seeing the quarks inside. That's not the kind of question you ask. Okay? So there's a historical reason which has to do, just with the fact that this is generally how we learned about a lot of physics. Okay. However, there are also some good theoretical reasons. Okay. There had to be, right? Otherwise, we would have considered these things even whatever our experimental friends did. Okay. So, so what are the good theoretical reasons? There are good theoretical reasons to consider the S matrix, and let me tell you about two theoretical reasons, which might not be very clear at this point. Okay. But I'll explain. I'll explain this again several lectures from now. Okay. You see, the S matrix is a kind of an unambiguously defined observable. Okay. It's an unambiguously defined observable because it only makes reference to what happens in the free theory. Is unambiguously defined, and this is not something that as opposed to that, this kind of question where you ask something slightly different. To answer this kind of question, what you might want to ask is, here's a state psi, and can I measure the correlators phi x1, phi xn in the state psi? To answer this kind of a question. Okay. Now the point is that if you're asking this kind of a question in a regime where all the fields are interacting with each other, okay, it's not quite clear what you should call the field phi. Someone might say, well, I call this field phi to be some quantity, and I want to call that the field phi. But if the field is interacting with something else, somebody might say, well, I don't like that definition. I want to call phi plus phi squared by 2 the field phi. Okay. As opposed to many other setups where maybe you want to talk about a height field on the ocean. That's kind of unambiguously defined, right? There's some height. Right? But quantum fields are not unambiguously defined in that way. We want to say there's an electron field or there's some electric field. But someone could say, well, I don't like to formulate things in terms of the electric field when it's interacting with other fields. And I like to formulate things in terms of electric field plus square of something else, magnetic field. Okay. And it wouldn't be quite clear, when the fields are free. In fact, in the case of the electric and magnetic field, it's kind of clear. When the fields are free, when they don't interact, it's clear that which field you can talk about, or different. There's a free field, and E plus B squared doesn't obey the free field equations of motion, whereas E does obey the free field equations of motion. So it would be clear which one to talk about. But when the fields are interacting with each other, then none of these fields anyway obey the free equations of motion. Right? So it's not clear how to choose what degrees of freedom to talk about. In some kinds of field theories, in particular what are called conformal field theories, there are other principles that allow us to choose what kind of degrees of freedom to talk about, and then we can ask these questions. But in general, the S matrix is unambiguously defined, and so in many quantum field theories, that's a good question to ask, which doesn't depend on choosing a basis for what kind of fields you're looking at. Okay. The second question is, and especially in ICTS, in quantum gravity, maybe only the S matrix makes sense. Okay. And the reason for that is that this kind of question, involves asking some local questions about what's happening in some local regions of space-time. Right? But when you're asking questions about what happens in quantum gravity, and the metric itself is fluctuating and space-time itself is fluctuating, these questions might not be so well defined. However, what remains well defined is still this kind of a question where you go far away, out to infinity, where things aren't fluctuating too much, and then you crash stuff from there and you ask what comes out. Okay. So both when you're far away and when in the far past and the far future, things simplify. And even in quantum gravity, that kind of a question might make sense. In fact, that kind of question is that kind of ambiguity in these kinds of local observables is kind of a refined version of what's happening here. It's the fact that what you call the field kind of depends on how you define it. And so there are good reasons to consider the S matrix. And so from the next lecture, we'll start considering interactions, but we'll spend a lot of time focusing on these kinds of interactions, where you ask what happens when you go in the very far past and come out in the very far future. And a lot of the field theory technology that we'll develop will be developed and will be geared towards computing these kinds of observables. Okay, and this is maybe a little bit of a disappointment from what you can do in quantum mechanics, and even what you do in classical mechanics, where you basically ask whatever question you like and you have a good answer. And of course, such questions also have a good answer in field theory, but it's much harder to compute, and these things are easier to compute. And there's also this, as I said, a good reason to focus on the S matrix, because it's a well-defined quantity, and these things are subtle to define in interacting theories, the more general kinds of observables. Okay, so I'll stop here. If there are any questions, I can take them. Otherwise, we can start a new topic next time.
Sir, in the Noether theorem, we use continuous symmetry. Is there any way for the discrete symmetries like baryon number? Because you said in the last lecture it is accidental symmetries.
No, sorry. So the baryon number is also an example of a symmetry of this kind. It's after all number conservation. Since you haven't discussed the standard model Lagrangian, I can't tell you in detail what it is. But it's a symmetry of the kind that existed in the previous board. Okay? It corresponds to rotating the phase of some of the fields in the standard model. Okay, so it's in the end, it's a question of conserving some number. That's what charge conservation is also doing. Right? It's conserving some number of particles minus some other number of particles. The fact that it's an accidental symmetry has to do with the fact that you can write down terms that would violate baryon number conservation, but it so happens that the leading terms you write down would be irrelevant. Okay? They would be irrelevant in that they don't matter at low energies, and therefore within the fields that we have in the standard model, if you go to low energies, baryon number is conserved. But this is something which is way out of where we are right now. So I'm not sure what is the motivation for this question. No, we haven't discussed any of what would be important to understand this question.
Sir, I asked because I thought that if we can replace integration with sigma and differentiation with the difference like del, and if we can like for discrete things, if we can make some equations from Noether's theorem.
This I didn't understand. What was the question? I did not understand.
Sir, I thought in Noether's theorem we are using differentiation and integration and all, but instead of differentiation we can make difference equations, and instead of integration we can make sigma, and I mean, is there any way so that we can make it for discrete things?
We could. You want to ask a different kind. You want to ask what if the theory is not. What if the symmetry is not continuous, but if it's discrete, and can you do something like this?
Yes, exactly.
Then we can't, right? Because the structure of group theory that we have here is rather rigid. So groups have continuous transformations. You can't think of. I mean, so if you have discrete symmetries, you don't have this kind of another charge. Yeah.
Okay.
The fact that you have a big discrete symmetry. Now, what you're talking about is a big discrete symmetry, but you still will not have another charge for that.
Yeah. Okay, got it.